You know, some stories are so huge, so famous, they almost feel like myths. And the sinking of the Titanic is definitely one of them. But what you might not know is that this very real tragedy is also a story about a surprising, fundamental exception in the laws of physics, an exception that's hidden in plain sight in every single glass of water. They called it the Ship of Dreams. I mean, it was a modern marvel of engineering, and everyone from the public to its creators called it unsinkable. That one powerful and, well, ultimately tragic nickname really set the stage for one of history's most famous disasters. Can you just picture it? April 10th, 1912. Crowds are cheering on the docks in England, people waving goodbye. So much excitement and hope in the air. As that giant whistle blew, the Titanic, the grandest ship the world had ever seen, steamed away on its very first voyage, heading out into the open Atlantic.
But just 4 days later, deep in the North Atlantic, the sea was just eerily calm. There was no moon, and that stillness was actually the danger. With no waves breaking against it, the iceberg was practically invisible in the dark until it was way too late. A lookout spots a shadow, the alarm goes off, but the ship is just too big, too fast. It wasn't some loud, dramatic crash, but more of a quiet, fatal, grinding tear along the ship's side. And in just a little over 2 hours, the unsinkable ship was gone.
The human cost was just staggering. More than 1,500 souls were lost that night, swallowed by the freezing, dark waters of the ocean. A terrible tragedy, really, born from a mix of human overconfidence and one single chance encounter in the dark. But let's just pause the story right here for a second and ask a kind of weird question. We all know icebergs float, right? But what if they didn't? What if ice behaved like almost every other solid thing on Earth and actually sank in its own liquid? I mean, think about it. In that alternate world, the ocean's surface would have been totally clear. There'd be no iceberg to hit, no collision, and no tragedy. Which brings us to the real mystery we're diving into today. What exactly makes ice float in the first place? To answer that, we have to leave the vast, dark ocean behind and zoom in. I mean, way in. Down to the invisible world of molecules, where the secret of water is hiding. So, meet our main character, a single molecule of water. It's actually incredibly simple. Just one oxygen atom stuck to 2 hydrogen atoms, and it makes this tiny little V shape. Billions and billions of these make up just a single drop of water. Now, the force that controls how all these little molecules interact with each other is called a hydrogen bond. You can think of it like a special kind of magnetic pull that makes water molecules arrange themselves in a very particular way, especially when things start to get cold. This slide shows the difference perfectly. On the left, in liquid water, the molecules are like a jumbled crowd at a concert, all packed in tight and constantly sliding past each other. But when water freezes, those hydrogen bonds kick in, and they lock all the molecules into this really orderly hexagonal crystal structure you see on the right. And this is the crucial part. That super organized crystal structure actually creates more space between the molecules. It's like they're holding each other at arm's length, creating all these tiny, empty gaps inside the ice. So this seemingly tiny detail at the molecular level leads to a huge and very, very rare exception to a general rule in physics. And it's an exception that had massive consequences on that cold night back in 1912. So here's the punchline. Because ice takes up more space, more volume, for the same amount of stuff, its density is actually lower than the density of liquid water. And in physics, it's a simple rule. Less dense things float on top of more dense things. It's really that simple. And I really want to stress just how weird this is. Think about almost anything else, like liquid metal cooling into a solid block, or melted wax hardening. In almost every single case, the solid sinks in the liquid. Water is one of the very few things in the known universe that breaks this rule. And this one little exception, it isn't just some random piece of science trivia. It has these profound, massive consequences for our planet, for all life on it, and yeah, for human history too. See, because ice floats, our lakes and oceans freeze from the top down. And that top layer of ice acts like a protective blanket or a warm coat, insulating the liquid water underneath from the freezing air above. This is what allows fish and countless other living things to survive the winter. If ice sank, our oceans would freeze solid from the bottom up, and life as we know it, it probably wouldn't even exist. And that brings us full circle. The very same principle that protects all that life in a frozen lake is what put a massive mountain of floating ice directly in the path of the Titanic. A tiny detail of molecular structure, that simple hydrogen bond, played a key role in one of history's greatest tragedies. It just goes to show you, sometimes science isn't about memorizing formulas from a textbook. It's about looking at something you see every day, like an ice cube in a glass of water, and just having the curiosity to ask a simple question. It really makes you wonder, how many other profound secrets are just hidden in plain sight, shaping our world in ways we can't even imagine?
All those secrets are just waiting there for us to stop, to look a little closer, and to ask the most powerful question in science and maybe in life: why?